figured it out, but
good. Okay.
they're like some kind of secret priesthood because it somehow hasn't propagated to the rest of us very well.
I see. Okay. Because I read a thing in physics today, maybe like 5 years ago, and then in the letters, it was sort of like, no, this is not solved. There's all these arguments about it.
Yeah.
About it, the guy. It was Zurek, the other Zurek,
Yeah,
Wojciech Zurek from
yeah.
Los Alamos, I guess.
Right.
And he called them cat states. Presumably because cats are like super classical, which I disagree with, but okay.
I think in some sense, this high priesthood, they got so into this that they look at really sophisticated questions that to the rest of us would be like, I don't even care, because they've figured out sort of the basic issue of, what does it really mean when you do a measurement dynamically?
Oh, good. Okay.
But then they go off into all this really super sophisticated, complicated stuff that I don't care.
Have they written any kind of, lay physicist's guide to?
It's frustrating because it ought to be just in the regular textbooks by now, but there are some reviews that I found that the first 2 pages were understandable, and I lifted some stuff today from one of those, and I'll have the citation, but
okay,
it's hard.
Oh, I see.
Yeah.
But after that, they define a bunch of math stuff, and then
yes, then they go off on terms of master equations, and they have this whole language that I don't care. You don't care either.
Okay. Okay. Okay, we're at 9:02 and 43 people connected, so maybe we wait. Oh, it's 9:03. Maybe we should get started. First thing in the morning is always tricky, but this will encourage students to show up on time. Yeah.
Yes.
Oh, there's actually a couple of questions already in the chat. One is about references for this topic, and
yeah, so I will give a reference that I actually used when I post the notes for today, which is a review paper, and I could only understand the first 3 pages, but the first 3 pages were really good.
Okay.
Use that as the basis for today.
All right, good. Okay, maybe we get started then. All right, welcome back everybody. Good morning to Joe Lykken from Fermilab's second set of lectures on quantum information science for particle theorists. Please go ahead.
All right, so welcome back. This is what we're going to try to do today. I'm going to talk a little bit. I want to talk about quantum information for real now, including some basic concepts like the density matrix and entanglement entropy, which I will define for you. But before we talk about quantum information, we need to talk a little bit about classical information. And I remind you of a few facts about ordinary classical entropy. And I also want to talk a little bit about classical measurements, because before we talk about quantum measurements, we need to remind ourselves of how we actually in the real world do classical measurements. And I'll give you some examples to remind you what that really means. So then I'll talk about the density matrix, which is a big deal, and the entanglement entropy, which is where all the interesting stuff happens. And that'll give us enough ammunition, formalism, that we can then have a discussion about quantum decoherence. So this is something, if you're John Martinez and you're building quantum computers, this is the whole thing you care about, because you've gone to all this trouble to make these fancy quantum states that you can put into fancy superpositions and manipulate them in any way you want. But you're always fighting this phenomenon of quantum decoherence, which is that by definition, your system of qubits is interacting with some environment. It's sitting on a chip somewhere. And that environment wants to spoil all of those fancy quantum superpositions that you built up and that you want to manipulate in order to do a quantum circuit. So I want to study the dynamics of how quantum decoherence actually works. And I'll do it in the qubit language. And I'm going to show you some experiments. These experiments are not in a Python notebook. They're in a Mathematica notebook, which I will post tonight. I don't know if everybody connected has access to Mathematica, but if you don't, you should, or find a friend that does, because as a particle theorist, it's super useful to be able to do things in Mathematica, even simple stuff like what I'm going to do today. But anyway, I'll go through it and show you what the results are if you can't look at the notebook. So the first experiment will be just using 1 qubit as my system and 1 qubit as my environment. So that's the simplest possible thing you could look at where something is interacting with something else. And we'll see that's not actually good enough to see something that looks like quantum decoherence. But then I'll do another experiment, experiment 2, where I'm going to have 1 qubit that I care about and then a 2 qubit environment. And already in that simple case, you'll start to see the basic phenomenon of quantum decoherence. And then that will give us enough confidence to go on to experiment 3. We're going to talk a little bit about measurement, which, as you'll see, quantum measurement is just a special case, obviously, of how an environment interacts with the system, right? It's sort of intentional, the intentional case where the environment interacts with the system because I want to measure the system. Okay. So let's start with some classical stuff. In fact, let me remind you what classical computers do, because people that do classical computing like to say it's really fancy and sophisticated what they're doing, but in the end, it's really kind of trivial. Every classical computer that anybody ever built that does anything, at the end of the day, all it's doing is it takes some input that's in the form of some number n of binary bits, zeros and ones, and then it does something, and then there's an output, and the output is also some string of maybe a different number of binary bits. And then the something that a computer program does, because it's just operating on bits, you can always express it if you want in terms of some sort of Boolean logic operations, right? Because that's arithmetic with bits is all ands and ors and nots and exclusive ors and stuff like that. So every computer that classical computer that anybody ever built or ever will build, this is what it's doing. And that's all it's doing. It's not doing anything else. Okay. And this is why when we talk about classical information, we always just measure classical information in terms of binary bits. So classical information is pretty simple. It's bits. For example, if you have the collected works of William Shakespeare, you are the proud possessor of, I counted it up, it's 16,800,000 bits, which is kind of a depressingly small number for the collected works of Shakespeare. Okay, so now let me remind you about classical entropy. So this is something we all learn in statistical mechanics. Entropy is kind of the flip side of classical information. And the person that had the big insight there was Boltzmann, and he wrote this famous equation, which I'll write. This is the only time I'll write his constant, Boltzmann's constant. So he wrote a formula that looks like this. So the entropy is some constant times the log of capital omega, and capital omega is just counting. And what is it counting? It's counting microstates, some states in some classical sense, because this is all classical. And these are the states of the system given that you fixed something. And the thing you fixed, if you're a classical physicist, is you fixed some values of some classical system variables like temperature. You said, this is the temperature, this is the pressure, this is the volume, something like that. And then given that, the entropy is counting all the states that could be there given those fixed values. So that's all I need to know about classical entropy. There is a more sophisticated version of this, which has grown up in the last half century or so. And this I would call modern information theory. And the person that invented this was Claude Shannon, one of these real singular genius types. And in fact, he invented what we now call Shannon entropy. And Shannon entropy is defined with a slightly more sophisticated formula. It's a sum over possible states of your system. Some probabilities, which I'll label by p sub I. A logarithm. Now I'm going to be careful about logarithms. From now on, every time I take a log, I'm taking a log base 2, which is the conventional way that people do things in information theory, including quantum information theory. Log of pi. So how do you compute something reasonable out of this? Let's take the simplest possible case where I'm doing some classical manipulation that involves probabilities, and that's our old friend, the coin flip. So I flip a coin. Let's suppose it's a fair coin, so it comes up heads 50% of the time and tails 50% of the time. Then the Shannon entropy for that is what? There's an overall minus sign. There's a 50% chance it turns up heads, so that means that p is a half. So I need a half times the log 2 of a half. And then the only other thing it could do is it can come up tails, and it does that also half the time. So the total of that is just minus log 2 of minus of 1/2. But of course, log base 2 of a half is minus 1. So, sorry, let me fix this. Equals minus. So log base 2 of a half is minus 1, so minus that is just 1. So what we have learned from this simple example is that a fair coin that comes up 50% heads and 50% tails has Shannon entropy equal to 1. And that actually is the maximum entropy you can have for a two-state system, for a single classical bit system. And what it's telling you is that you don't know anything. You have no useful information about what's going to happen when you flip the coin. And in fact, I can say in general that if I have n bits, the maximum Shannon entropy is always n. So if I have n bits and my Shannon entropy is n, it means I don't know anything about this system of n bits. Now you can have other cases. For example, suppose you have a coin that's been fixed so that it always comes up heads or it always comes up tails. That's the other extreme, right? So that would be the fixed coin. Oops. Notability is too smart for its own good sometimes. All right. So that means, let's say that the probability of it coming up heads, which I'll call P of H, is equal to 1 instead of a half. So what's the Shannon entropy in that case? Well, if I have a probability of 1 times the log of 1, the log of 1 is 0. So the Shannon entropy is 0. And what if it's fixed the other way? What if the probability of heads is equal to 0? That kind of configuration here gives me a log of 0, which is technically infinity, but fortunately it's multiplying 0, which is more of a 0 than that divergence. And so by our convention is that also gives S equals 0. So that makes sense too, right? Because if the coin is completely fixed, then I know everything about it. I know exactly what's going to happen with 100% certainty when I flip the coin. So the only interesting case is the in-between case where somebody gives me a coin and they tell me, well, it's not completely fixed, but it's biased. Then what do I do? So if I have the intermediate case, and I'm a classical physicist, I know what to do, right? You start flipping the coin. So I can make this a little more rigorous by saying that before I start flipping the coin, I will assume what I call a prior probability, which is that it's an ordinary coin. So I'll assume, since I don't know anything until I start doing the measurements, that probability is a half because I don't know anything, so I might as well, it's just as likely that it's heads or tails. But now I start flipping it, and I do it many times. And now I'm gaining information, right? I'm gaining classical information because I did the experiment and I did it many times. So then as a result of that, I can update my estimate of what probability of heads is. And we call that the posterior probability because it's now presumably an improved estimate because I did gain information by flipping the coin many times. So this is what classical measurement is. All classical measurement comes down to doing this. Here's a little diagram that summarizes what I was just saying. So in the intermediate case, the Shannon entropy is not 0 and it's not 1. If it were 0, then I don't need to do anything. I already know everything. If it's 1, I'm doomed because flipping a fair coin 100 times doesn't tell you anything because it's still just as likely to come up heads or tails as before. But where I learned something is in the intermediate case where the Shannon entropy is somewhere between 0 and 1. And now I can try to gain information about what's going on by doing the measurement. So let me give you an example that's maybe a little more sophisticated. So let's now do classical measurement in general. And I'm going to use the LHC, the large Atlas and CMS experiments, as an example of that. And I want to, in fact, it's important for you to keep in mind that the measurements we do at the LHC, contrary to what you might think, are classical measurements almost completely. So classical measurement theory is indeed the right theory to use if you want to do measurements at the LHC. So what's the first step? First step, this is the funny thing about classical physics, is you, the observer, you have to choose your system variables of interest. In quantum mechanics, there's a fixed set of quantum numbers, and you can choose which ones you're interested in, but you can't choose what they are. They are what they are, nature tells you. But in classical physics, you have a lot more options. And to give you an example at the LHC, we very often choose as some of our classical system variables something called jets, which is something that we then go in and count and measure inside, say, the Atlas or CMS detectors. But nature doesn't know what a jet is. This is something that you, the observer, made up, and you defined it. And in fact, if you go talk to people in Atlas and CMS, you will find out that the thing they call jet in Atlas is not the same thing that they call a jet in CMS. They are different things. They're defined differently. It has to do with different properties of the detectors. So an Atlas jet is a classical system variable, and a CMS jet is a different system variable. But by going in and measuring things about jets, we learn things about the underlying physics, including ultimately the underlying quantum physics. But it's classical measurement theory. So you go tell me what you're interested in. I want to measure jets. I want to measure, even an electron at the LHC is not what you would think. It's not the electron of the standard model. It's a complicated thing that has to do with stuff you see inside the detector. So you go choose all that stuff, okay? What else? Well, in general, before I do the measurement, I already know something. And so I have some prior knowledge. And in general, that prior knowledge is in the form of a probability distribution because my prior knowledge is uncertain. Furthermore, after I do my measurement, in general, my information will still be uncertain because I didn't learn everything that I could possibly have learned. And so when you do a classical measurement, what you're actually doing is you're taking your prior probability distribution, doing a measurement, and then using the information from the measurement to try to get a better probability distribution. Which we call the posterior. This is something that even collider physicists at the LHC had kind of a hard time wrapping their heads around. And in the early days of the ramp up to the Higgs boson discovery, in those days I was working in CMS, and you wouldn't believe the kinds of arguments that people had about this, because most of us had not been raised to think about measurements in this language. And the thing that would led to zillions of arguments had to do with something called Bayes' theorem. And what Bayes' theorem is it's a way of computing the following quantity, P of X given Y, where X is the system variables you're interested in, and Y is the results of some measurement that you did. And I'm gonna, when I post the notes, I'm gonna post a little problem, a problem set that leads you through what Bayes' theorem is and how you actually compute things using it. But it's only been relatively recently that the high-energy physics community has accepted what should have been the obvious fact that this is how you do measurements, because the measurements we do 99% of the time are actually classical measurements, and this is the right way to do them. So it's a probability distribution, you do a measurement, you have information, you use that to update to another probability distribution. I think the case where we're all familiar with this, talking about classical physics in terms of probabilities, is when you talk about thermal ensembles, right? This is the one where we're all used to it. You have the Boltzmann distribution, it's Boltzmann again, and he says, okay, you know the temperature, but that doesn't really mean you know what every atom in the box is doing. And so if you want to describe things that are happening in a finite temperature system, you have to talk about a classical ensemble of possibilities. And then those Boltzmann weights are telling you the probabilities of various kinds of things happening. So that's the notion of a classical ensemble dealing with probabilities. Okay. All right, so after our review of all of classical physics, including the LHC, we're going to talk about the density matrix. So this is going to start out with a very important statement. If it's the only thing you remember from these lectures, it's probably the most important thing to keep in mind, even though it's obvious. In the real world, which is the one we live in, all quantum systems are open systems. That means that there's a piece you're interested in, which, since it's quantum, it has some Hilbert space of states. That's the stuff you're interested in. So that's the Hilbert space of interest. But then there's always an environment. I'll call that capital E. And that also has a Hilbert space, usually much bigger than the one that you're trying to measure things in. And these things are interacting because there's physics. So why do I say this is an important statement? Because the way we teach quantum theory and the way that we do it in practice, we almost never take into account explicitly that the quantum system that we're interested in is part of an open system. We treat it like a closed system. If I have a discretized problem, I say the Hilbert space has some dimension n, and that's it, and the rest of the universe doesn't matter. Very often that's a good approximation, but it's already a bad approximation if you ever want to measure anything. And this is where you get into trouble in the way that we teach quantum mechanics, because if measuring something means interacting the thing that you're interested in with an environment that includes the measuring apparatus. And the way we usually get around this when we teach quantum mechanics is, I think, extremely confusing and misleading for everybody, including me when I learned it, is we just sort of postulate, well, there's this other thing called measurement, and when you do that, this is what happens. But of course, what really happens is there's an interaction with the environment, and as a result of that, information moves around and things happen. But we need to understand now this in a little more detail. And why is that? Because now we are interested in quantum computers, and in a quantum computer, this is exactly the interesting question. I have some qubits. I want to do something with those qubits, but then I want to know what happened. So I need for those qubits to interact with the environment in a controlled way in order to measure them. And I also am worried that before I get around to measuring them, that the nice superpositions that I set up will be destroyed by interactions with the environment that I don't control. And the beauty of thinking about this for quantum computers is that interactions with very, very simple environments, and I'll give you an example that's a 2-qubit environment, is already enough to destroy your quantum computer. So when you look at people that are doing research on how to build quantum computers, they talk about the problem of 2-level systems, meaning that there's something in the environment that's just a single qubit that they don't know about and that they can't control that will screw up the qubits that they're interested in the quantum computer. So quantum computing is a beautiful way to actually look about what's really happening in general when you have quantum open systems. Okay, but we need a little bit of formalism to do that. So in particular, what we're going to do now is we need to generalize, because we're talking about open systems, the idea of a classical ensemble, which is the way in classical physics, as I just reminded you, we deal with open systems and uncertainty there. And we have to generalize that now to some sort of quantum ensembles, because now I want to talk about how my quantum system interacts with its environment, including variables that aren't under my control and that I don't observe. And we know there's going to be a big problem, because if I have a classical ensemble, I can separate things any way I want. But in quantum, when you try to separate the whole system, S plus E, into a piece that's just S, you know you're going to get into trouble with entanglement in general. So I need a way of generalizing the idea of classical ensembles to include the effects of entanglement. And as I showed you yesterday, the effects of entanglement are not necessarily short range. They will be short range, but in addition, as we saw in the extreme examples we looked at yesterday, they could be extremely long range. And I'm going to answer a question now, which is, except maybe the quantum universe of the system, which I suppose is closed. This is a very interesting field of research. So I claim that everything we do in quantum physics is open systems, but what if I take the whole universe? Isn't that a closed system? And the answer is, we don't know how to answer that question. And there is actually my colleague, Andy Albrecht, was one of the first people in my generation to look at this question seriously. It's a really interesting, difficult question. So if you're interested in that, you can actually make a career out of thinking about that. All right, so now I told you we have a challenge here, which is how do you generalize the notion of a classical ensemble to include the effects of quantum entanglement? And the answer is you use something called the density matrix. And I'll actually start out by writing something called the density operator. And what this does is it describes ensembles of quantum states. Rather than classical states. And what does that look like? So density matrix, you always write it with the Greek letter rho. It's a sum over states, some weight, which is actually probability, P sub I, and then a projection operator onto some particular state psi I. So remember in this Dirac notation with the bras and the kets, if you put the ket before the bra, that's a projection operator onto that particular state, psi I. Write it this way. Okay. So that's what a density matrix is. So why do I say it's an ensemble? It's an ensemble because I've summed over not just a single quantum state, but several quantum states with probabilities. That's not the same thing as a superposition. Now, more generally, I've written this in a particular basis, but the actual density matrix itself depends on your choice of basis. So suppose I change from this basis, these basis states psi I, to some other basis by some unitary transformation, which I can always do, right? Then this same version of the density operator in general, so here's the more general form, it'll look like a sum over two indices, I and j, of some rho ij of some ket psi I with some bra psi j, where I and j are not necessarily the same. And it's in fact this version, which is the version you get in a more general basis, is how we extract the density matrix. The density matrix is just these coefficients rho ij here. So that is in fact a matrix. And it's a matrix whose dimension is the same as the number of basis states you have in your system. Okay. So it has a couple of obvious properties, this density matrix. It's Hermitian because of the way we constructed it. Its trace is equal to 1. So that was obvious from the first way I wrote it, because the first way I wrote it in terms of a sum of weights, which are probabilities, and over some complete set of states. So the sum of those had better be equal to 1. Another way of saying this is that if you just consider the density matrix as a Hermitian matrix, then I can diagonalize it. It's got some eigenvalues. Those eigenvalues are real. But in fact, since those eigenvalues have the interpretation of being probabilities, they had also better be non-negative. So that's another feature of a density matrix. And then just to give you a couple of examples, let's suppose I have just one particular quantum state. So let's go back to the case of everything you've ever done in quantum physics up until now. That always involved talking about individual quantum states. Those quantum states in general are quantum superpositions, but as I said yesterday, I can always go to a basis where whatever your state was, psi, I can just take it to be one of my basis states. So forget about superpositions. You give me any state you want, and I'll just take that to be one of the basis states of some orthonormal basis that I can define. And then in that language, the density matrix of just having that one state can always be written in this trivial form. It's just a diagonal matrix with a 1 somewhere and the rest zeros, right? Because by assumption, when I just look at closed systems, which is what you're normally doing in quantum theory, you don't have an ensemble, you just have one quantum state. So there's only one non-zero entry in the density matrix. And that, of course, has trace equal to 1 because there's only one non-zero eigenvalue and it's equal to 1. And in this language, we say that ordinary quantum states, the ones that you've been using for your entire life so far, are called pure states. Meaning that in that case, you don't actually have an ensemble of quantum states, you just have one particular state. It's convenient sometimes, since I'm not always in the basis where I can see this immediately, to look at another quantity, which is the trace of the square of the density matrix. And you'll see in this trivial case where I just had a pure state, an ordinary quantum state, that not only is the trace of the density matrix equal to 1, but the trace of the square in this case is also equal to 1, right? And that turns out to be a convenient way that doesn't depend on the basis to tell whether or not you have a pure state. So if somebody gives you a density matrix that looks super complicated because they chose a super complicated basis, you can check immediately to see whether it's secretly a pure state just by taking the trace of its square. And if the trace of the square is equal to 1, then it's just a pure state. If it's
There's
less,
a question in the chat.
yeah, go ahead. First way.
Yeah, the question says, is the first way of writing rho a classical density matrix? I think
Yeah,
referring
so-
to on the previous page.
So you can, I mean, other than the notation here that involves projection operators and things, you can think of this original notation that had the probabilities as just the completely straightforward extension of the way you define a classical ensemble, right? The way I define a classical ensemble is I just say I have some way of writing classical states. I don't know what it is because there's lots of ways of doing classical physics. And then I sum over them with some probabilities. So this is using exactly that kind of reasoning, but now we're applying it to a way that makes sense in quantum mechanics where you have some fixed Hilbert space, you've got some fixed basis states, and you have to write things in terms of that quantum language. But the idea is indeed like a classical ensemble. Okay. So remember this criterion because we're actually going to use this later. In fact, I'll give you some simple examples now of the other case. So the only other thing that can happen with density matrices, besides having a pure state, is you have a quantum ensemble. And in that case, we say we have a mixed state. So that's jargon, but it's standard jargon. So everything you've done your whole life with closed quantum systems was pure states. And now you have now opened up a whole nother world that you can describe with density matrices that includes mixed states. All right, so why is that good for anything? Now this allows us to do some real investigations that will turn out to be quite interesting, where I can see the effects of the environment upon S. So S I always will call the system. It's the thing that I'm interested in. If you were doing closed quantum systems, that's what you would call S. But now we're going to take into account that there's some kind of environment that does something. So the thing that turns out to be interesting to do with density matrices is to take what are called partial traces of them. A partial trace of a matrix is a well-defined thing. In fact, in the Mathematica notebook that I'm posting today, there's a Mathematica routine that does partial traces for you so that you don't even have to pay attention to the next 5 minutes. You can just press a button and it'll do the partial trace for you. But let me explain to you a little what this means. So let's take the simplest possible example. I have a system that's a single qubit and it's going to interact with an environment that also has a single qubit. And let's assume that they are maximally entangled. They're not just interacting, but they're maximally entangled. So this is like one of our Bell states that we talked about yesterday, 0, 0 plus 1, 1. So what's the density matrix for the whole system in that case? So if I look at the density matrix of the entire system, that should be that's still a pure state, right? Because now I've treated the bigger system like a closed system with the pure states in it. And I can construct its density matrix. And this expression here, it's going to be 1 over square root of 2 times the ket 0, 0 plus 1, 1. And then times 1 over square root of 2 times the bra of 0, 0 plus 1, 1. And then if you just think about that in terms of a matrix, that should be matrix language. It's a 4 by 4 matrix because I've got 2 qubits now. So that Hilbert space is 4 dimensions. So what 4 by 4 matrix is it? Well, its non-zero elements are going to be the 0, 0 part of that matrix. That's coming from 0, 0 with 0, 0 here. So this guy with that guy. So that gives me this element. I could have 1, 1 with 1, 1. That gives me this element. But I can also have 0, 0 with 1, 1. That gives me this element. and I can have 1, 1 with 0, 0. That gives me this element. So this is a perfectly good density matrix. Its trace is equal to 1 because the 1 over square root of 2's give me a 1/2 out front. So the trace is indeed equal to 1. That's good. Otherwise, we'd be in trouble. So now I'm going to take this perfectly good density matrix of a perfectly good pure state in the larger system, and I'm going to take a partial trace over the states in the environment on the theory that in the real world, I don't know what the environment is. So I shouldn't be trying to write down the state of the environment because I don't have any access to it. So how do you do that? You take that 4x4 matrix and you take the trace over just the second qubits part of the state. So now I'm labeling the qubits now in either S or E. That's either the first or the second qubit. So that's just an ordinary trace of this rho sub SE, this density matrix, but it's a trace just in the states of the second qubit, which are either 0 or 1. So that's this expression here. If I can get, okay. So now what do? I can take, the easiest way to think about this so you don't get confused is to write the density matrix again in terms of this Ket-Bra notation, and just stick the density matrix written in terms of Ket-Bra notation inside these two matrix elements here. So what do I get if I do that? The only things that can give me a non-zero answer is when, since I'm in this guy, I had better have zeros for both my environment qubits. But that means because of this maximal entanglement that I'll have zeros for the system qubit. And then the only other thing that can give me a non-zero contribution is if I have ones, all ones for the environment qubit. But then because of the entanglement, that means I also have ones for the system qubit. So do those trivial matrix elements, you get to this next line, which is just what I just said, that the system qubit, the part that survives this partial trace, it's either 0, both of these guys 0, or both of these guys 1. So now I've taken the 4x4 density matrix that describes system plus environment, and I've written a partially traced density matrix that's 2x2 that describes just the system. And this is what that matrix looks like. It's 1/2 times the identity matrix. That's also a perfectly good density matrix. It's got trace equal to 1. But this is not a pure state. And you can see that in a variety of ways, but an easy way to see it is just to take the trace of the square of this matrix. What's the trace of the square of this matrix? The square of this matrix is this, which is just 1/4 times the identity again. And the trace is equal to 1/2. So in fact, unlike a pure state where the trace of the square of the density matrix is 1, when you have a mixed state, the trace of the square is less than 1. And in fact, the worst it can be is 1/2. And we now have the worst case scenario because we've chosen a state that has maximum entanglement. So this is, if you like, a maximally mixed state. And in fact, this density matrix that I've written here looks like what I would have written classically as a density matrix, if you like, for a coin flip. It's just saying there's a 50% chance you're in 1, there's a 50% chance you're in 0, and it doesn't even look quantum anymore. And in fact, I can't tell the difference anymore. It just looks like an ensemble. And that makes sense because this is a maximally entangled with the environment. If I don't allow myself to know anything about what's happening in the environment, but the environment is maximally entangled with the system, then really I don't know anything about the system either.
There's a question about the algebra up above it. Somebody just made a comment that maybe it looks like there's some extra ones.
Oh, so yes. So let's see here. So I think the unfortunate thing here is that the way I draw 1 looks exactly like the way I draw a vertical line when I'm making bras and kets, I think is the problem. And I may even have drawn too many lines. I think I have the right number of lines, but that's That's the issue. It looks better with the zeros. Sorry about that. This is one reason why I have LaTeX all my notes, because my handwriting is terrible, and so the LaTeX is the only solution to this problem. So I will post the LaTeX version of this afternoon. Okay, so remember the partial trace, because we're going to be doing that now quite a bit. All right, so let's move on and talk about entropy in the quantum system. So we talked about Boltzmann entropy. We talked about Shannon entropy, which is the fancier version of Boltzmann entropy. And now I want to talk about how you can actually measure entropy in a quantum system, taking into account the effects of entanglement. The formula for this is, I don't know if it was derived by von Neumann, but it's called the von Neumann entropy. And it's also called the entanglement entropy, and I'm going to use that language because I think it's more descriptive of what is actually going on. And von Neumann's sufficiently famous that I don't feel like I have to say his name all the time. So this is the formula for entanglement entropy as a function of the density matrix. So the density matrix is rho. You see, it looks very similar to what we did with the Shannon entropy, except that now instead of putting in probabilities from some distribution, we're putting in the full density matrix and taking minus the trace of the density matrix times the log base 2, because remember, we're always doing log base 2 of the density matrix. So now I'm going to give you simple examples of how that works. Let's take the case that we were just doing. So suppose I have rho is equal to 1/2 times 1001. So how do I compute something like rho log rho? Well, the way to do it is in terms of the eigenvalues of the matrix. So here the eigenvalues of the density matrix. It's got 2 eigenvalues, they're both equal to 1/2. So S of rho in this particular case is equal to an overall minus sign. The trace just says do it with the first eigenvalue and then do it with the second eigenvalue. So this formula should look familiar to you. It's the same formula I wrote for the Shannon entropy of a coin flip. It's exactly the same formula at this point, and it's equal to 1. And that's the confirmation in terms of entanglement entropy of what I told you about this system, that once I take the 2-qubit maximally entangled system and I only allow myself to know something about the first qubit, then really I know nothing. Because what's happening here is that when you have 2 qubits that are maximally entangled, they are sharing their information. Let me write that down because that's an important thing to remember. Maximally, entangled.
Joe, there's a question along those lines.
Yeah. So the state is, if I understand it right, the state is mixed because it's maximally entangled and we don't know what our system will do to this coupling. Am I right in this kind of thinking? Yeah, so when you talk about open systems, this is also true classically. It's not just that you're not looking at the environment now and maybe you'll look at it later. You're admitting that there's only part of the system that you have access to, and therefore it can do whatever it wants. And then you have to somehow account for the fact that you don't know what it's doing in detail. So
I think it might be worth saying that you have to be really careful how you define state, right? So like, if you say my state is the system plus the environment, then no, it's a pure state. But if you say my state is the system and not including the environment, then yeah, it's a mixed state.
So you're insisting on only looking at a part of the real dynamical system. And of course, we're always doing that in physics, right? Because in physics, that's all we can do. But sometimes it matters that you're restricting your attention to part of the systems, and sometimes it doesn't matter. In this case, because of entanglement, it matters a lot that you're only looking at part of the system. So if I were a classical physicist, I would say that these two qubits are sharing one bit of information. Here they're sharing, to be precise about it, 1 qubit worth of quantum information. And this is really what quantum information means. We've now finally gotten to the point where you can start to see what I mean by quantum information. I mean precisely this. I mean that in this case, which is an extreme case, I have 2 qubits. I would have thought that that's 2 qubits worth of quantum information, but it's not due to the entanglement. It's really only 1 qubit worth of quantum information. Now, if I had done the same calculation for the environment, if I had taken the partial trace over the system, so let's suppose instead of doing S of what I computed for you here was the entropy of rho sub S after I trace out come on. Okay. What I computed for you was the entropy of the system after I traced out the environment. I could have instead traced out the system to see what is the entanglement entropy in the environment. And you would find in that case the same answer. You will always find the same answer when you do that. And that's why I say they're sharing the information. It's not that the environment has the information and the system lost it. And it's not that the environment has, the system has the information and the environment lost it. They're sharing the information. And that you can see by computing these two guys. Another way of saying it, and this is something that I'm not really going to use, but it's very handy for people that are doing real research, is you can define something called the mutual information. That's the information they're sharing in some sense. And that's defined, in this case, it would be S of rho subsystem, entropy of the system, plus S of rho sub environment minus S of the combination. So that's, I'm not going to use that, but just in case you want to pursue this further, that's another way of looking at this. And then last but not least, before we go off onto the next topic with our experiments, I wanted to, I was mentioning this at the beginning today, I wanted to mention that when you have mixed states like this, as a result of entanglement, as you saw in this case, you can represent those states, the density matrix for those states, in terms of the block sphere. But what you will find is that those states are living not on the surface of the block sphere, which is where pure states live, but they're living in the interior of the block sphere. And so to summarize that, mixed states can be represented by points at some radius. I'll take the block sphere to have radius 1. So that's the interior of the block sphere. And that is directly related to the fact that there is entanglement. And to prove that, here is the formula which you can derive. In fact, I'll probably post this as a second problem for the problem set to guide you through how to derive this. You can actually derive the entanglement entropy for a mixed state in terms of this radius of where it lives on the block sphere. This is something that's done in the nice book by Eleanor Reifel, which I highly recommend, and I'll have a reference to that when I post the notes. So I claim that the density matrix is a way of generalizing your usual way of talking about quantum physics in terms of pure states. And you see that now in a kind of geometrical way, that the pure states were just the surface of the Bloch sphere, and you lived your whole life on the surface of the Bloch sphere. But now, the real world involves, if you like, states that in general live in the interior of the Bloch sphere.
Joe, there's another question.
Yeah, here's a question about if you compute the entanglement entropy of the combination 4x4 density matrix, you find that it's 0. What does that mean? Very good question. So in the case where I assumed, as I've been assuming here, that my system plus my environment, that I've been assuming that was a closed system, just to keep things simple. And since I assumed it was that the combination was a closed system, its entanglement entropy is 0. Because I know, think about the coin flip example. I know everything about the system. I've assumed it was a closed system, and to the extent that that's a good approximation, its entanglement entropy should be 0. Now, of course, again, in the real world, that's never exactly true, but I've made an approximation there. Thank you, good question. All right, are we ready to do experiments? I want to do the experiments. That's the funnest part of this. So the first experiment, I'm going to try to look at this phenomenon of quantum decoherence. This is how the environment interacts with the system and does things that maybe you don't want it to do, especially if you're a quantum computer designer. So I'm going to try the simplest possible example, and it's going to fail to do what I want it to do, which is to destroy my quantum computer. But it shows you the basic physics, and in fact, it's a practical interest. So I'm going to take a case where we have one qubit system, and we have one qubit of environment. And now I'm going to let the qubit interact with the environment through a particular Hamiltonian, because it's quantum physics, right? So I need some kind of a Hamiltonian for the system environment interaction that involves two qubits. And I'm going to model this on something that's called the Jaynes-Cummings Hamiltonian, which has to do with something, an actual way of building quantum computers. So in that way of thinking, the system qubit is two levels in an atom, two quantum states in an atom. That's my qubit. And the environment is the fact that photons can interact, and the two-level atomic system could either absorb a photon, in which case it goes from the lower energy state to the higher energy state, or it could emit a photon, go from the high energy state to lower energy state. So that's a simple interaction. I can write it in terms of a Hamiltonian that looks something like this. The first qubit now is my atom, and the second qubit is my photon. So I'll put one term in my Hamiltonian that represents the fact that, in fact, this two-level system has different energies. There's a lower energy and a higher energy. So there's some energy splitting. And I can use the poly-Z matrix as good enough to represent that. And then I need some interaction that tells me that the photon can do something. So what's the something? Well, there's two things that can happen. I can either be in the higher energy atomic state and emit a photon, or I can be in the lower energy state and absorb a photon. So these two terms represent those two possibilities. And here I've used these little matrices, sigma plus and sigma minus, that they either raise or lower you or destroy your state, depending on what state you're in. So that's a very simple Hamiltonian for two qubits. I've motivated it in terms of this Jaynes-Cummings Hamiltonian, which is a little fancier, and you can look it up in the references that I'll provide. But this is an actual kind of a thing that you do when you're thinking about quantum computers. Okay. All right, so now I've got a Hamiltonian, that's good. Now I have to put these two qubits in some initial state. And then I'm gonna let the Hamiltonian do some time evolution. So what's my initial state? I'm gonna take that, this is for the two qubit system at time t equals 0. So I'm gonna take that to be, I'm going to take my first qubit to be in the 0 state, and I'll take my second qubit to be in the 1 state. So one way of writing that is to use projection operators. This is a handy way of writing this kind of stuff. So this is P10 here says that for the first qubit, I can define a projection operator onto the 0 state, which written as a 2x2 matrix is just this matrix. This says, give me 1 if I'm in the 0 state and give me nothing otherwise. And then this guy, P21, says a similar thing for the second qubit. It says, I want to make sure that I'm in the 1 state. So I take 0, 0, 0, 1. Okay. And the tensor, this cross with a circle around it is tensor product. So that's one way of saying what our initial state is. And that's some simple 4x4 matrix. You can work out what that is. It's easy. And now I've got a Hamiltonian. So I need some unitary time evolution operator. It's e to the minus IHT. So I construct that. What is that? That's a 4x4 unitary matrix in this 2-qubit system. And then what am I going to do? I'm going to take the density matrix at time t equals 0, and I'm going to hit it on both sides with this time evolution operator, with u on one side and u inverse on the other side. And that will give me the density matrix at some later time of the whole system. Okay, so it's basic time evolution, quantum mechanics, nothing new there. So far we haven't done anything new, but now we want to do a partial trace. So now I want to define, using the density matrix of the whole system at some time t, I want to define just a density matrix at time t for the single qubit system variable, the thing that I'm interested in. So how do I do that? I figure out what rho of the whole system is at some time t, and I do the partial trace. Okay? So you can work this out. It's in the Mathematica notebook. It's real simple for that Hamiltonian that I just wrote, and I'll write what the answer is. It's a 2x2 matrix because the system is a single qubit. I'm going to take the coupling constants that I wrote down, a couple of coupling constants here. I'll take them equal to 1. C1 and C2 are coupling constants. I'll take them equal to 1 to make this easier. And then the partial trace gives you 1 plus co-squared square root of 2 times t in that diagonal entry. And it gives you zeros off diagonal, and it gives you sine squared square root of 2t in the other diagonal. So that's really simple. It depends on time. Not entirely obvious what's happening here, but let's make a plot now of a couple of quantities. And so all I'm doing now is taking this partially traced density matrix. So this now describes at any time t what I will see if I only allow myself to know about the system qubit and I don't know anything about the environment qubit. So this is what you'll find in the mathematical notebook that I posted. And here I plotted two things. The orange line as a function of time is the entanglement entropy of just the density matrix for the single qubit S, our system qubit. And you see that it starts at 0 because I started with the system qubit in some known pure state, started with it in the state 0. So its entanglement entropy at that point is 0. But now you see that as time goes on, its entanglement entropy varies with time. And in fact, there are some times where it's equal to its maximum value of 1. But then there's other times it's actually periodic behavior. Not surprising because this is the result of a time evolution with e to the minus IHT. So it's periodic, but sometimes the entanglement entropy is the maximum value, other times it's in between, and other times it goes back to 0. And the other thing I plotted here is the trace of the square of the density matrix of just the system, rho s. So I'm applying the trace of the square. And remember, that's the quantity which, if you have a pure state, it should be equal to 1. So indeed, it starts out at 1, because we started out in a pure state. And in the worst case scenario of maximal entanglement, it can be as low as a half. And indeed, in the cases where the entanglement entropy is equal to 1, this quantity is equal to half. But again, it's oscillating up and down and back and forth. So this is actually a slightly non-standard version of something called Rabi oscillations. And I don't know if they were invented by Rabi, because it's always dangerous. Things get named after, there's a theorem that things are always named after the wrong person, but that's what they're called. And this is not quantum decoherence, right? Because even though there are times where things are maximally entangled, which you would have said was decoherence, because you would have said, now the environment has screwed me up and I don't know anything anymore. There are times it's periodic, so it goes back and forth in reality. So it's not quantum decoherence, but it certainly is interesting dynamical behavior where you see entanglement happening and then undoing itself between the system and the environment. And in fact, Rabi oscillations is one of the ways that you make a quantum computer. Because think of what I'm doing here. I took a two-state atomic system, and now I want to put it in a more interesting quantum state. And if you have control of the photon, which was my environment, you can actually use that photon to get the atomic system into a more interesting quantum state, as you see here. So this is, not only is it not quantum decoherence, it's actually one of the tricks that people designing quantum computers use in order to manipulate the qubits that they're interested in and make them do things. Here, I've actually represented it in such a way that I've emphasized the bad part, which is that these oscillations, at least at certain times, can look like you're getting maximal entanglement between the environment and the system. So this was an attempt to show you quantum decoherence that failed, but it failed for the obvious reason that if my environment is too simple and I do ordinary unitary time evolution, all that ever happens is that things oscillate, and they may oscillate to interesting ways, but all they do is oscillate. Okay. So now we're going to do experiment 2. And experiment 2 is interaction with the 2-qubit environment. So this is actually conceptually exactly the same as what I just showed you. And the only thing is that instead of having 1 environment qubit, I'm going to have 2 environment qubits. The Hamiltonian has the same kinds of interactions. Qubit 1, which is my system, can interact with environment qubit 2, but it can also interact with environment qubit 3. And I added a couple of extra terms just for fun. But it's conceptually.
There's a question in the chat about the previous example.
Is each minimum corresponding to the atom oscillating from spin up to spin down? That depends on what I am exactly I'm doing with my atoms. In principle, the thing I had in mind here was an atom where the 2 states are just 2 energy eigenstates. And I'm not interested in the spin, but there are indeed people that are doing this with the spin. So it depends on the details of you can do it that way so that it spins. Thank you, that's a good question. Spins are a way to do these kinds of qubits. All right, so experiment 2 I'm gonna do really quickly because it's exactly the same as experiment 1, except I have 2 qubit environment instead of 1 qubit environment. And also this is now sufficiently complicated because now it's an 8x8 matrix that I'm not going to do it for you by hand, and I didn't do it by hand, I did it in Mathematica, and so I'm going to show you the answer. Okay, but conceptually it's exactly the same as what we just looked at. And now I'm going to look at 2 things, but I'm going to look at something that we hadn't looked at before, which is very important for quantum measurement. I'm going to look at the entanglement entropy. So here's the orange now is the entanglement entropy of the single qubit that's my system imaged in. And you see now it starts at 0 because I started off in some pure state. And then it's kind of wiggling around, but what it's tending to do is to get large and then stay there. So that looks more like quantum decoherence. right? Because what is quantum decoherence? Quantum decoherence is I start out with a pure state that's, say, a qubit state of my quantum computer, and then there's some characteristic time scale where it has become so entangled with the environment that I should shut off my quantum program because it's no good anymore. That's what we mean by quantum decoherence in a quantum computer. And that's because you've got so much entanglement now with the environment that I no longer have control over what I'm doing. And this is in fact what happens when you run quantum computers. If you run the Google quantum computer, you will find that approximately 100 microseconds after you start your quantum circuit, you can't use it anymore because of exactly this kind of effect. And when I say exactly this kind of effect, I really mean exactly this kind of effect, because it's not known precisely what the environment is that's doing this in real quantum computers, but it involves probably just a few states, a few very simple states that of the environment that are interacting with my qubits. And that's important in the example that I'm showing you here, because if you actually extend this example, and you can do this in a Mathematica notebook, to larger times, you will see that eventually the entanglement entropy goes down again. And that's because this is still such a simple environment that it doesn't really want to just do one thing. It wants to get back and oscillate at some point. So I've kind of cheated you in showing you this behavior, but I haven't really cheated you, because this is already enough if you're a quantum computer to ruin your program. So very simple interactions with the environment, even if eventually they would correct themselves, are enough in a real quantum computer to give you quantum decoherence. Now, in fact, typically environmental interactions involve very large numbers of degrees of freedom, in which case this is exactly what happens. The entanglement entropy quickly goes to 1 and it just stays there. Now, the other thing that I plotted here in the blue is I have a 2x2 density matrix for my system qubit, and it has an off-diagonal, 2 off-diagonal matrix elements, right? So it's a 2x2 matrix. Let's call it A, B, C, D. That's row of S. And the off-diagonal matrix elements are telling me that at least in this basis, I have some kind of superpositions. I don't have a state in this basis that's just a 0 or just a 1. So an interesting thing to ask is what happens to those off-diagonal matrix elements when I turn on the interaction with the environment? And here you see that in this case for this Hamiltonian, that even though the off-diagonal part starts out large because I took my initial state to be a superposition in this case, that over time the tendency is for the off-diagonal guy to go to 0. And this is a common feature of the interaction with the environment. And this is actually very important, because this is telling you that the interaction with the environment can take a state that's a superposition and turn it into a state that effectively is just either a 0 or a 1. And the fact that in the real world physics of the dynamics of things, that this happens is very important, because of course, this in the end is how you do measurements. You do measurements by actually finding states that have the property that when you measure them, they give you either 0 or 1. They don't give you a superposition of 0 or 1, right? When I look at the dial on my meter, I don't want to know that it's a superposition of 10 volts and 100 volts. I want to know, is it 10 volts or 100 volts? So we design measurement apparatus to have this property that even if in principle they could be in a superposition of 2 measurement values, in reality, if you wait 1 picosecond, the answer is either 0 or 1. Here's a question which I'm going to answer. So if the environment has large degrees of freedom, when my system oscillate back to the pure state eventually? But it's such a long period of time that at that point you can forget about it. This actually gets into this sort of the behavior of chaotic systems, if you know something about that, that once you start to get large degrees of freedom, if you think about it as sort of orbits in phase space, you can get these orbits that essentially never come back to where they started from. And that's a feature. It's not a quantum feature. It's a feature just of anytime you have large numbers of degrees of freedom. Okay, so I just want to point out that Wojciech Zurek was one of the first people, at least, to realize that this is a very important feature of everything we do with quantum mechanics. And he even gave a name to these states. He calls them pointer states. So states which in principle could be in a superposition, but in reality, due to dynamics, at the end of the day, are not in superposition. They're either 0 or 1. He calls pointer states. And this is a fact of the dynamics of nature that such states exist. And in fact, they're not the exception, they're the rule. This is the typical thing that happens. A good example of this is energy eigenstates, right? We usually don't worry when we have energy eigenstates about them being in superposition. And that's because it's really hard to get them in superposition and maintain them for any period of time. It's in principle possible, but such superpositions are very unstable. If I'm a quantum computer designer, I need my qubits at the end of my quantum circuit to be pointer states, because when I say that I measured them and they were 0 or 1, I need to be able to do that. I need them to manipulate them in some such a way that they're either 0 or 1 at that point and not a superposition. And this has to do, how you actually do that in terms of taking a measurement is something that I'm not going to do today because I ran out of time, but that'll be experiment number 3 that I'll start with next time. So to summarize, what I wanted to get across today was quantum information. You can think of it as classical information. So it's like classical entropy. It has to do with your ignorance of things, which involves probabilities, even classically. But then it has this additional feature of quantum entanglement. And quantum entanglement gives you new, interesting things that can happen that you wouldn't see in the classical case, and make quantum information actually a much richer subject than classical entropy. So that was point number 1. Point number 2 is the density matrix is everything. If you really want to teach quantum mechanics, you should teach it with the density matrix, because the usual wave function that we teach everybody is just a special case. The density matrix is the more general thing. In fact, it's an interesting feature of the density matrix that the usual overall phase that we have in the wave function, and then we say, yeah, there's an overall phase, but it doesn't really matter. In the density matrix, that overall phase cancels out. So the density matrix even looks more fundamental than the wave function. And it is, in some, it's certainly more general, and I would even assert that it's more fundamental than the usual wave function description. So that's the second point. And then the third point is this point about quantum decoherence, that every quantum system is an open system. That means there's always dynamics with the environment. And in general, quantum dynamics means entanglement. And the effects of entanglement in the environment are not only real, they're measurable, and they're important because they are relevant to things like how you do measurements of quantum systems. So that means every particle physicist needs to know this, because this is very basic, fundamental of what you do as any quantum physicist. So why don't we quit there for today if there's any more questions?
There is a question which is in the chat, but I wanted to ask it also. Aren't my off-diagonal elements basis dependent, and how do you find which basis states the environment prefers as pointer states?
Yes. So this is a very,
on the Hamiltonian.
So if you look at the literature on this, the parts of the literature that are understandable, which is a small fraction of it. So there's a whole industry of people that look at quantum measurement theory, which includes talking about quantum decoherence, obviously. And I haven't found a good introductory review, although I think somebody in the chat suggested one. But the basic example they like to give of pointer states is energy eigenstates. And this kind of makes sense, because think about the interaction of the system with the environment. It involves an interaction Hamiltonian. So let's suppose I just focus on that interaction and I forget about the Hamiltonians of this system and environment separately. Let's suppose the interaction is the thing that dominates the dynamics. Then that's a Hamiltonian. And there's some operators that commute with that Hamiltonian. And so if I set things up in a basis that commutes with, that's eigenstates of that interaction Hamiltonian, then of course, those are pointer states, because now when I turn on the time evolution, if I started with them in the state 0, they stay in the state 0. So it is certainly a feature of the quantum dynamics of the interaction between the system and the environment that you should have pointer states, because there's always something that commutes with the Hamiltonian that's connecting the two things. So pointer states are certainly a generic feature. Energy eigenstates are the most typical example of pointer states, but they aren't the only example. I don't know of a classification for how to think about this in a more general way. I only know about examples, but it certainly is a rather generic feature of the way dynamics works.
So would another way to answer that be you just take your Hamiltonian and you make this plot in various bases until you see what you want?
Yes.
I mean, okay, the dumb way to do it. Then
Yeah.
the smart way to do it is find the commuting operators.
Yeah, the problem is, and in general, I don't know the Hamiltonian for the interaction with the environment, and I may not even know what the environment is.
Okay, fair enough. Yeah.
And
Okay.
quantum computer was the example, right? If you ask John Martinez, after 100 microseconds, your circuit dies because it interacts with the environment. What is the environment? He says, I don't know. I don't actually know what is the physical state on my chip that this thing is interacting with, and I don't know what the interaction Hamiltonian is. And that's the typical problem that you have.
Okay, one more question. It seems like the density matrix contains both classical and quantum information. Classical info because mixed states are described as by classical probabilities. What would the classical analog of the density matrix be?
So the classical analog that's the closest to something you've already done would be something like a Boltzmann thermal ensemble, right? So that's something where you just say, I've got a bunch of possible states. All I know is the overall temperature. And so I'm just going to assume that any of those states is possible, but it's possible with some weight, and that weight is e to the minus beta times the energy, where beta is 1 over kT, right? That's how you make a Boltzmann ensemble. You can even do that with quantum states, right? You can say, I've got a finite temperature quantum system, and I can make a Boltzmann ensemble out of those guys. So one way of answering your question is to say, if the only thing I was ever interested in was thermal ensembles of quantum states, could I do that with the density matrix? The answer is yes. In fact, I've been screwing around with things like that myself. It's interesting for things like finite temperature early universe calculations. You actually end up doing things like that.
Yeah. And then the last question, how do we know, okay, not the last question. How do we know energy eigenstates of the system are also eigenstates of the interaction Hamiltonian? I guess it depends on the interaction Hamiltonian.
That's right. So I was taking the simplified case where the interaction Hamiltonian actually dominates the full Hamiltonian, but that doesn't have to be the case, right? If the interaction Hamiltonian is just a small perturbation of the full Hamiltonian of the system, then it's a different story. So again, it depends on as usual in physics, it depends on the details of the dynamics.
And then someone's asking about, does the Born rule come from decoherence?
Wow, I don't know. I'll have to think about that. Oh yeah, here's somebody pointing out that there's a relation here between the density matrix and the partition function, and that is indeed correct. And when I said I'm fooling around with things like this, that's exactly what I've been fooling around with.
Oh, I think the question about the Born rule might be related to, no, maybe not. The trace of, I was going to say the trace of the square of the density matrix, but I think that is totally irrelevant. Okay, all right. Something to think about for tomorrow, maybe.
That's a good one. You stumped me on that one. I have to think about that one.
Okay. Okay, so we're at 10:20, or sorry, yeah, we're at 10:24. And I think we should thank Joe again and give people a break, and we resume at 10:45 with whoever is next, who I will tell you in a second, with Shifang on collider physics.
Right.
All right, thank you, Joe.
Thank you.